Today we're going to be talking about rotation. Yes, that's the new thing. And so here is my fun and exciting video on, let's try that rotation again. Why am I still doing that? Oh my goodness, Mansky, do better. All right, third time's the charm. Rotation basics. Because up until now, you've done everything like in a straight line, stuff like that. You've done a little bit of spinning with circular motion, but now we're going to talk about, well, what happens if just everything is rotating? All right, so we're first going to start off with a kind of visual aid here. So we've got a little pretty diagram here. It's circle. Yes, I'm cheating, I know. Don't judge. And then we've got this doot. And we're just going to kind of work our way through here. So here's our angle that we are rotating through theta. We are going to start at kind of this point right here, and we're going to rotate in that direction. And obviously this is a circle, because if you're rotating, everything's kind of a circle. So there's our radius. And now we're just going to talk about what are the basics. So if you look at an object that is kind of spinning, then you think of it like, hey, well, the radius of the object is constant, but our angle is going to change over time. So like our angle is kind of where we are, so that's going to keep changing as we spin. And then if you think like that, well, we used to have, hey, I'd go in a straight line, but now we're spinning. So instead of traveling a distance, we're going to travel an arc length. All right, so that's kind of this segment right here. That's our arc length. We call that S. So, we kind of use S and X kind of interchangeably at this point, but S is kind of our arc length because we're moving through part of a circle. Now, a few things we want to understand here is that we measure our angles in radians. It's that stuff that your math teacher told you need, and you're like, I'll never need this. It makes no sense. Well, we use it in physics when things start rotating. So when you're talking radians, you got to remember that 2 pi radians is equal to 360 degrees. So what that means is that pi by itself is 180 degrees. So if you ever need to convert from degrees into angles, you're good to go. Also, if you think about it, we defined in math class your arc length as S. So that's how far that arc is. And that's equal to the radius times the angle that you're going through. Okay, so this is kind of important. I'll just, bust out a highlighter on that. Boop. All right, so that's kind of important. Now, if we then use this analogy of linear things to rotational things, we can start going to other stuff because this is effectively our distance. All right, that's effectively our distance. And so now if we move into the other stuff, remember that we defined velocity as your distance changing relative to time. Now, because we're going to also be working with integrals and derivatives, we don't just use the delta. What this really means is velocity is the rate of change in your position over the rate and change in your time. So dx dt. That's the worst x ever because I was going to write a t. My brain died on me. Sorry. So dx dt. That's so much better. Oh, whew. All right. So instead of changing the position with respect to time, we are going to be changing our angle with respect to time. And thus, for this, we talk about not linear velocity, but angular velocity. So that's how your angle changes with respect to time. We give that the symbol omega, the lowercase omega. It looks like a W, but it's not. It's an omega. And so this means our change in our angle with respect to time. All right. Now, some key things we want to talk about just to remind ourselves here. When we're talking about this, we measure the angular velocity is in radians per second. Instead of meters per second, it's in radians per second. And so if we think about how this all kind of works down, then it is the velocity divided by radius, because if you look at your units, you got radians per second, velocity is meters per second, and we have to get rid of that meters. All right, so then that really means is that omega is equal to velocity divided by the radius. And so if we rearrange that, because that's what we will be doing, it means that velocity is equal to your angular velocity. So this would be your tangential velocity. I'll jot that down a second. And I shouldn't write omega r. I should write r omega. All right, so that's another key thing here. So we're kind of make analogies between linear understanding and angular understanding. All right, so this right here, this t, this would be your tangential velocity. So if you were to check your velocity at a specific point in time, that's what you get. All right. Now, if we say, okay, so I've got now my distance kind of understood, and now I've got my velocity understood. Well, what about acceleration? Good questions. Oh, these are solid questions you're asking, yes. So acceleration, all right, so I'll go up here. We got some more space. Acceleration is defined as your change in velocity per unit time. Well, we know that that is equal to now dv dt. And if we look at our angular acceleration, it's just like our the derivative of our angular velocity. It's the exact same mentality. So if we go to angular acceleration, it's going to have that same understanding, except instead of be dv dt, it's now d omega dt. So it's the rate and change of your angular velocity per unit time. And just like before, if we look at our units, so we'll just do a quick unit look here. Acceleration is meters per second squared, but angular acceleration is just radians per second squared. So that means in order to get rid of this m here, we have to really divide all this by our meters, and meters is our radius. So what that means is your angular acceleration, which has this beautiful alpha, is equal to the acceleration times your radius. All right. I always switch the A and the R there, but c'est la vie. All right. So we now have our kind of our three analogous equations to what we used to have in terms of our linear acceleration, linear velocity, and linear distance and displacement. All right, so let's kind of just summarize that. So let's scroll down here a bit and let's just summarize. So if we look at all this, oh, wait, before I summarize, one more thing I forgot. Let's go back. Boop, 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 boop. Remember that we have centripetal acceleration from circulars, and that was equal to velocity squared divided by radius. You remember that. It was good times. You guys love that unit. So we got v squared over r, and now we have a new definition for velocity. So I can take this and I can put it in here, and so I can now do AC, instead of being equals v squared of r, it's r squared omega squared divided by r, which obviously that's going to nuke out that. So we have a new definition for centripetal acceleration in terms of angular velocity, and that would be omega squared times radius. So you probably want to have that in the back pocket as well. All right. So there we go. I want to do that. I almost forgot about that. So now let's go back to that summary of our analysis. So far, rotational, we have, like I said, we've made direct analysis and direct analogs, I should say, between distance, velocity, and acceleration. So let's just kind of put those all in one spot so we can see it. So if we are going to look at this in terms of linear, we have x But in terms of angular, we have theta. All right, so our x becomes a theta. And then our velocity, v, which you're going to see I might get a little fancy now. V becomes omega. And then acceleration becomes an alpha. And we have equations that link these two together. So x, which again sometimes is just an s. All right, it's not multiplied, it's just an or. So you'll see it written like this in textbooks. So our equation then is s equals r omega. Linear velocity or tangential velocity is equal to your radius times your angular velocity. And your linear acceleration or tangential acceleration is equal to the radius times your angular acceleration. All right. So these equations, mas importante, they're going to what links us together. Now, if you think about it, since we are making links between linear motion and angular motion, we can bust out all of our old kinematics equations. I know, you're like, oh my God, I thought I was done with those. No, we can go back to our kinematics equations. So you guys remember these. So again, linear, EA. I'm sure there's other letters in there. We'll just, no, come on, you can do better. LIN, became a science teacher for reasons. EAR. I skipped it up here too. I don't know what's going on. All right, so linear, we've got the kinematic equation, V sub naught plus AT, V squared equals V sub naught squared plus 2A times your displacement. Displacement is equal to V sub naught T plus 1/2 AT squared. And we also know that displacement is equal to 1/2 times V sub naught times T. So these are all of our kinematics equations from linear motion when we were just doing, intro physics. Well, now we have angular analogs of these. All right, so here's our angular analogs. V is replaced with omega. So instead of having V's, we have omegas. So omega is now equal to omega sub naught plus, instead of having linear acceleration, we have angular acceleration. So that's one equation. So now we've got omega squared equals omega sub naught squared plus 2A times your angle here. And then we've got your angle, or I should say your change in your angle, which is how much you've rotated, is equal to omega sub naught T plus 1/2 alpha T squared. And finally, your change in your angle is equal to 1/2 omega plus omega sub naught times T. So as you can see, we have it's just plug and play, okay? So it's just a direct replacement with our old kinematics equations. So all of these are now our equations for angular motion. So this is angular kinematics. All right. So if you've memorized those linear equation, then you pretty much have the new angular ones memorized as well. So there's no real reason to freak out. The one last thing I do want to talk about before I get too crazy with this and we start going to, well, how do I apply this? How do I use this? Is direction. Okay. Now before we had like up, down, left, right. And so we'd say, hey, up is positive and right is positive and the other two are negative, but in reality, we could choose that frame of reference. Well, here for direction, we need what's called the right-hand rule. All right, so this is mas importante. This is called the right-hand rule. Now, with the right-hand rule, which I'm just going to RHR, in case I need to jot that down in future reference, you basically take your fingers. And this is where, I'm going to show it to you in class, but you basically take your fingers, and so here's your hand. All right, you take your right hand, so you've got a thumb. This is going to be the worst drawing ever. Don't judge me. All right, so you've got here's your hand, here's your thumb, palm. All right, so there's your hand. Thumb is up. That's really ugly. And so what you're going to do is you're going to curl your fingers around. All right, so your fingers, like I said, you're going to curl your fingers around. You're going to basically make a fist-ish. So let's see if I can do this. Thumb, curled finger. I mean, it's not horrible. I've seen worse. My daughter can do so much better than me. All right, so you're going to curl it around. And then whichever way your thumb is pointing, all right, your thumb tells the direction. And you're curling your fingers around the way it's rotating. So for example, this would be like a disc that's rotating here. And let's say the disc is rotating in this direction on this axis right here. Okay. So then you'd curl your fingers around, and then this would be the direction of your rotation. So that'd be the direction of your acceleration, the direction of your angular velocity, things like that. So we use what's called the right-hand rule to figure out direction. Then you basically say, okay, I'm calling this positive, and you'd be like, hey, I'm calling this positive, yay. And then that would mean this is a negative. If it was, in case you have multiple things rotating, you got to try and make some comparisons. So that's the right-hand rule. Okay, so this has just been our intro to rotational motion. So hopefully it kind of clarifies that we're not going too far off the rails here. We're going back to what we know. We're just making links to all the stuff that we know very well. So I hope you found that helpful. And yeah, I'll see you guys in class.